Okay, this is a practical looking at the refraction of light. And it's going to look at trying to quantify Snell's law. And let me just write down what that is. In effect, you have an incoming light beam usually from air into something more optically dense, or something which light travels slower in, glass, for instance. And then you're looking at the change in angle from the normal, not the material, but the normal, the incident ray, and looking at how it is refracted. So you're looking at the refracted ray. We obviously know that the speed in air is c, it's the speed of light, but obviously it slows down as it goes into glass or something more optically dense. And the ratio of those speeds is known as the refractive index. Now, Snell's law, what it does is it tries to quantify how much that angle changes by. So we have this rule that says sine I over sine R is equal to the refractive index. I won't go through the proof. I think I've done that in another lesson, a video lesson. I'll put a link below. Good, so what are we going to have to do? Well, in order to test this theory here, we're going to have to get a range of incident angles, and then we're going to have to measure a range of refracted angles, and then we're going to have to do this sine function, this mathematical function to it. So what I'm going to change is the incident angle, so that's going to be my independent variable, incidence, in degrees. And then we're going to look at the angle of refraction, and that's going to be measured in degrees. And then we're going to look at sine I, sine R, and then, though graphically we're going to prove this, I'm just going to put in another column, which is sine I over sine R, to see if that ratio looks something similar in the first instance. You could take repeats of these if you wanted to. I think my results came out pretty well without having to do repeats. But that's the table of results, and that's how we're going to conduct it. Okay, let's show you how this has gone about. First of all, we need some sort of light source. I'm going to use a laser box here. It's really quite useful. I can get one nice straight beam. That's a laser beam out of here. It could be used with a light box or any form, or even just a laser pen if you want, just held there. The nice thing about this is that it presents quite a vertical beam. The laser pen is just a precise column, if you like, so it's quite hard to keep it aligned, whereas this is a nice long vertical beam that comes out. And then I'm going to look at it as it goes through. This is perspex, but still more optically dense. So if I line up that diagram that I had, what I'm doing is I'm placing that there, and I'm shining light through this, following there, and you'll see a deviation. Not as much of a deviation as I've indicated, but there's definitely a deviation that goes on. So how are we going to do that? Well, I suggest that you draw in more neatly than I've done here. The reason why I've done this is in black pen is so you can see it on the video. But you draw around the glass perspex more optically dense block. And then, once that's done, with a protractor, draw in the normal, and then from the normal, you draw in lines at 10, 20, 30, 40, 50, 60 degrees. Then, when you place your glass block, optically more dense block there, and try and keep that as still as possible, because it's easy just to accidentally knock it. Once it's there, move things around it. Line up your beam with, let's just take the middle beam. Line up your beam from the point there to the point there. I don't know if you can see, but it's just there is the exit point. Just leave a dot, that's all that's necessary. Next one, make sure it's lined up perfectly. There's your dot. Let's try another one. Line it up as accurately as possible. There's my dot. And then when I remove that, if that's my normal, then all I need to do is join that dot with there, that dot with there, and if you're using a pencil, a sharp pencil, then you'll be able to get a much better measure for the refracted angle. So line this up with the normal, and then look at what your refracted angle is. Obviously, this one here will be the steepest, and so as you work your way down there, you can work your way up here from 10 degrees through to 60 degrees, 50, 40 degrees, 30, 20 degrees. I've got a little bit of space, so I'll just try and write that in there. And so we measure the outcoming angle. You've got to have pretty much, if you're looking at the 10, it's got to be smaller than 10, so that will give you another indicator. Good, and sounds pretty straightforward. There are the results that I gained. We can see that they're all smaller than the incident angle, which makes sense, and then we've taken sin I, sin R, and then looking at the ratio, which is not bad. I mean, when you look at it as a table, that looks, you think, oh, well, that's a bit varied, but when you plot a graph, however, then it makes life a lot easier. So how do we plot the graph? If you want to hit pause and copy those down, please do. Otherwise, let's talk about this graph. I'll use another bit of paper because it will make life easier. Here we go. Sin I over sin R is equal to the refractive index. Let's rewrite this. We want sin I on this side equals n sin R multiplied by y equals mx plus c. And of course, this is plus 0, so you can ignore that. So if I were to plot sin I against sin R, sin I on the y, sin R, then my gradient would equal the refractive index. Just here. Good. If you're a purist, or should I say a proper scientist, you'll probably say, well, this is the independent variable, so that should be on that side. Okay, if that's the case, then that's a valid point. Sin I, sin R, then your gradient should be 1 over the refractive index. Good, hope that makes sense.